Assalamualaikum everyone and a very good day to all. In this video, we shall learn about the schemes and techniques that we use to transmit data digitally. First, we will discuss digital to digital conversion techniques. This is the method which converts digital data to digital signals. We will also learn about line coding and the different types of coding schemes. Here is the table of contents for you to navigate through this video. Okay, so underlying coding schemes, we can categorize it into 5 different categories. So we have unipolar. Under unipolar, we have non-return zero, and then we also have polar. And under polar, we have non-return zero, return zero, and biphase. And polar, biphase, Manchester, and differential Manchester coding. And we also have bipolar. Under bipolar, we have alternate mark inversion or AMI and pseudo-ternary. We also have multi-level, 2B1Q, 8-bit, 8B60, and also for the PAM5. And lastly, we can have the last category is the multi-transition, which is one of the example is MLT3. So these are the schemes of line coding, and we need to be familiar with all the schemes discussed in this video for better understanding for the rest of the course. And this section can be used as a reference for schemes encountered later. The first line coding scheme that we will look at is the unipolar non-return zero, or short form is the NRZ. Okay, so better if we look at the figure itself so you would understand. You can use this slide for revision later on. In a unipolar scheme, all the signal levels are on one side of the time axis, either above or below, but typically we will have it above. So unipolar scheme was designed as a non-return to zero scheme. What does it mean by that? It means that the positive voltage is defined by bit 1 and the zero voltage defined by bit 0, and it does not return to 0 in the middle of the bit, as you would see in other line coding after this. Okay, compared to polar non-return zero, which you will see next, this scheme is very costly, as the power needed to send 1 bit per unit line resistance is double that for polar non-return zero. For this reason, this scheme is normally not used in data communication anymore. In polar schemes, the voltages are on both sides of the time axis. For example, the voltage level for 0 can be positive and the voltage level for 1 can be negative. So in polar NRZ encoding, we use 2 levels of voltage amplitude. And in polar NRZ, we have 2 types. We have NRZ level and also NRZ invert. NRZ level or NRZL is the level of the voltage determines the value of the bit. Whereas in NRZI, the change or lack of change in the level of the voltage determines the value of the bit. Meaning that if there is no change, the bit is 0, and if there is a change, the bit is 1. Okay, in terms of baseline wandering, it is a problem for both variations, but it is much worse, twice as severe in NRZ level. If there is a long sequence of zeros or ones in NRZ level, the average signal power becomes skewed, and the receiver might have difficulty in judging or distinguish the bit value. And in NRZ invert, this problem occurs only for long sequences of zeros, but not ones. Okay, and if you can somehow eliminate the long sequences of zeros, then we can avoid baseline wandering in NRZI. When sender and receiver clocks are not synchronized, it causes synchronization problem, and this exists in both NRZI and also NRZL. Again, the problem is more serious in NRZL or NRZ level compared to NRZ invert, because long sequences of zero cause a problem in both schemes, but long sequences of ones only affect NRZ level. Okay, NRZ, both schemes have an average signal rate of n/2 baud, and let's discuss the bandwidth. You can have a look at this figure down here. It shows the normalized bandwidth for both variations. The vertical axis shows the power density, meaning the power for each 1 hertz of bandwidth, and the horizontal axis shows the frequency. The bandwidth shows a very serious problem for this kind of encoding. The value of the power density is very high around frequencies close to 0. That means that they are DC components, and it carry a high level of energy. Okay, most of the energy is concentrated in frequencies between 0 and n over 2. This means that although the average of the signal rate is n over 2, but the energy is not distributed evenly between the two intervals. Okay, let's recall back what I said just now. In NRZ level, the level of the voltage determines the value of the bit, and it can be vice versa. If you know the value of the bit, then you would know the level of the voltage. And in non-return zero invert, the inversion or the lack of inversion determines the value of the bit, as you can see here. Again, if you remember, I mentioned just now in polar schemes, the voltages are on both sides of the time axis. So for example, in this particular example, the voltage level for 0 is positive and voltage level for 1 is negative. In terms of negative, it means that it is 0. Okay, so as you can see at the top here, the bit is 0, but we put it on the positive in the V. Okay, amplitude V, and then for bit 1 we have it at 0. Okay, as long as you defined it, make the assumption, whereas voltage level for 0 is positive and voltage level for 1 is negative, then it's fine. As you can see also here in NRZ level, again, the level of the voltage determines the value of the bit. Okay, and for NRZ invert, the change or lack of the change in the level of the voltage determines the value of the bit. If there's no change, like for example here from 0 to 1, there's a change, so the next bit is 1, meaning that for the second bit is 1, so there's an inversion in the level of the voltage. And then if there's no inversion, then the next bit is 0, or if you know that the bit is 0, that means that there's no inversion, and you continue. Okay, let's do an example on polar NRZ. A particular system is using NRZ invert to transfer 10 megabit per second data. What are the average signal rate and minimum bandwidth? So remember, average signal rate, or S, equals to n over 2 for NRZI. And if you substitute n with 10 megabit per second divided by 2, you get 500 kilobaud. And for the minimum bandwidth, B min equals to S. So in this case, B minimum bandwidth is 500 kilohertz. Okay, if you see the main problem with no return zero encoding just now, it's when the sender and receiver clocks are not synchronized. So the receiver basically does not know when one bit has ended and the next bit is starting. Okay, so one solution is we can use return to zero scheme, where we use 3 values, positive, negative, and 0. In return 0, the signal changes not between bits but during the bit. Okay, meaning that the signal goes to 0 in the middle of the bit. Okay, it remains there until the beginning of the next bit. Main disadvantage of return 0 encoding is that it requires 2 signal changes to encode a bit, therefore it requires greater bandwidth. The same problem we mentioned, a sudden change of polarity resulting in all zeros interpreted as ones and all ones interpreted as zeros. It still exists there, but there is no DC component problem. But in return 0, the complexity is also a problem because we use 3 levels of voltage, which means that it is more complex to create and also to discern. Okay, as a result of all these deficiencies, the scheme is also not used today. It is being replaced by the better performing Manchester and differential Manchester scheme, which we will discuss after this. Okay, in polar RZ, let's see an example. As you can see here, in this particular bit, it goes to 0 in the middle of the bit. Same goes to bit 1. In the middle of the bit, it goes down to 0. Okay, so again, as you can see here, we are using 3 different levels, positive V, 0, and minus V. And this causes more complexity, but it adds it helps to mitigate the synchronization problem. The idea of return zero just now, where we have transition at the middle of the bit, and the idea of no return zero level are combined into the Manchester scheme. In Manchester encoding, the duration of the bit is divided into two halves, and the voltage remains at one level during the first half and moves to the other level in the second half. And the transition at the middle of the bit provides synchronization. In differential Manchester, as you see after this, it combines the idea of return zero, which is the transition at the middle of the bit, and also non-return zero invert. There is always a transition at the middle of the bit, but the bit values are determined at the beginning of the bit. If the next bit is 0, there is a transition. If the next bit is 1, there will be no transition. The Manchester scheme overcomes several problems associated with non-return level, and differential Manchester overcomes several problems associated with non-return invert. In both schemes, there is no baseline wandering and no DC component because each bit has a positive and negative voltage contribution. The only disadvantage is the signal rate. The signal rate for Manchester and differential Manchester is double that for non-return zero. The reason is that there's always one transition at the middle of the bit and maybe one transition at the end of each bit. And the next figure will show you both Manchester and differential Manchester encoding scheme. Note that Manchester and differential Manchester scheme are also called biphase scheme, and the minimum bandwidth for these two schemes is 2 times that of non-return zero. Okay, let's see an example for Manchester encoding. As you remember, the duration of the bit is divided into two halves, and the voltage remains at one level during the first half and moves to the other level in the second half. Again, the transition in the middle is for synchronization. You need to make an assumption or define for 0 and 1. Like for example, in this particular case, we have from positive voltage towards negative voltage for bit 0, and we have from negative voltage to positive voltage for bit 1. Okay, so next we will see differential Manchester. Differential Manchester is when the bit values are determined at the beginning of the bit. Like in this case, if the next bit is 0, there is a transition. If the next bit is 1, there will be no transition as indicated by the legend at the bottom there. And regarding with the bandwidth, as you can see, the minimum bandwidth of Manchester and differential Manchester is twice that of non-return zero. Next, let's go to the third category, that is the bipolar. We have AMI and pseudo-ternary. In bipolar encoding, sometimes we call that multi-level binary. We have also another category called multi-level, but in this case, it's for binary multi-level. And in bipolar encoding, there are 3 voltage levels. We have positive, negative, and 0. The voltage level for one data element is at 0, while the voltage level for the other element alternates between positive and negative. Okay, there are 2 types, as I mentioned just now, AMI and pseudo-ternary. The common one is the AMI, which stands for alternate mark inversion. In the term alternate mark inversion, the mark actually comes from telegraphy, and it means 1. So AMI, in other words, it can be also understood as alternate 1 inversion. Okay, a neutral 0 voltage represent binary 0, and binary 1s are represented by alternating positive and negative voltages. A variation of AMI encoding, that one is called pseudo-ternary. in which the 1 bit is encoded as a 0 voltage and the 0 bit is encoded as alternating positive and negative voltages. Okay, so for AMI, the neutral 0 voltage represented by binary 0, and for pseudo-ternary, the 0 voltage is represented by 1 bit or binary 1. The bipolar scheme was actually developed as an alternative to non-return zero. The bipolar scheme has the same scenario as non-return zero, but there is no DC component in bipolar. The NRZ scheme has most of its energy concentrated near the zero frequency. If you remember just now, I mentioned that, and this makes it unsuitable for transmission over channels with poor performance around this frequency. The concentration of the energy in bipolar encoding is around frequency n over 2. As you can see in this figure, this shows the typical energy concentration for bipolar scheme. Why do we have DC component in bipolar encoding is because if you use Fourier transform, you can see the answer, but you can also think of it logically. Okay, so if you have a long sequence of ones, the voltage level alternates between positive and negative. It is not a constant basically, okay, because it will always alternate between positive and negative. Therefore, there will be no DC component. And for a long sequence of zeros, the voltage remains constant, but the amplitude is 0, which is the same as having no DC component. In other words, a sequence that creates a constant 0 voltage does not have a 0 component. AMI is commonly used for long distance communication, but it has a synchronization problem when a long sequence of zeros is present in the data. Later, you'll see how scrambling technique can solve this problem. Here you can see the example for AMI, where the 0 are represented by a 0 voltage and binary ones are represented by alternating positive and negative voltages. It's for the pseudo-ternary, we can see that for zeros it is the alternating positive and negative voltages, whereas the 1 bit is represented or encoded as a 0 voltage. Let's go to the fourth category under line coding, which is the multi-level schemes. If you remember, we want to increase the data rate, but we want to decrease the required bandwidth, and that is why we have all of these line coding schemes. Okay, one of the goals is to increase the number of bits per baud by encoding a pattern of m data elements into a pattern of n signal elements. So under data elements, we have zeros and ones, so there are only two types, which means that a group of m data elements can produce a combination of 2 to the power of m data patterns. We can have different types of signal elements by allowing different signal levels. So if we have L different levels, we can introduce L to the power of n combination of signal patterns. So if 2 to the power of m equals to L to the power of n, then each data pattern is encoded into one signal pattern. But if you have 2 to the power of m is lesser than L to the power of n, data patterns occupy only a subset of signal patterns. The subset can be carefully designed to prevent baseline wandering, to provide synchronization, and also to detect errors that occurred during data transmission. And data encoding is not possible if 2 to the power of m is greater than L to the power of n, because some of the data patterns cannot be encoded. So these code designers have classified these types of coding as MB and L, where M is the length of the binary pattern, B means binary data, N is the length of the signal pattern, and L is the number of levels in the signaling. A letter is often used in the place of L, or the level. Like for example, we have B for binary, for L equals to 2, or we have T, that is the ternary, for L equals to 3, and quaternary for L equals to 4. Note that the first two letters define data pattern and the second two define the signal pattern, meaning that the MB is for data pattern and NL is for signal pattern. So from previous slide, we can say that in MBNL schemes, a pattern of M data elements is encoded as a pattern of N signal elements, in which 2 to the power of M must be lesser or equals to L to the power of N. Okay, the first MBNL that we're going to discuss is 2 binary and 1 quaternary, or 2B1Q. B stands for binary and Q stands for quaternary, which uses data patterns of size 2 and encodes the 2-bit patterns as one signal element belonging to a 4-level signal. It is start encoding M equals to 2, N equals to 1, and L equals to 4. The next figure in the next slide will show you example of 2B1Q. The average signal rate for 2B1Q is S equals to N over 4, which means that by using 2B1Q, we can send data 2 times faster than by using, for example, NRZL. However, 2B1Q uses 4 different signal levels, which means that the receiver has to discern or need to distinguish or judge 4 different thresholds. Okay, the reduced bandwidth comes with a price because of this difficulty to discern the complexity. There are no redundant signal patterns in these schemes because 2 to the power of 2 equals to 4 to the power of 1. Okay, so there's no redundancy in the patterns, and the 2B1Q scheme is used typically in digital subscriber line technology to provide a high-speed connection to the internet by using subscriber telephone lines. So this is an example of 2B1Q. As you can see, it uses data patterns of size 2 and encodes the 2-bit patterns as one single element belonging to a 4-level signal. These 4 different signal levels also means that the receiver has to discern 4 different thresholds. But it also means that we can send the data twice faster as compared to NRZL. Okay, so you can also see that the rules are already defined there. So you can also see that it's actually using the gray coding where the successive values differ in only 1 bit or binary digit. So we increment a value from, for example, here -3 to -1. We require only 1 bit to change instead of 2 bits. Okay, again, you can see here one signal element is composed by 2 data elements, and so this is 2B1Q. You can also see that the bandwidth is also reduced as compared to before. Another line coding scheme under multi-level is called 8B60, whereas it encodes a pattern of 8 bits as a pattern of 6 signal elements, and the signal has 3 levels, which is the ternary, and this code is used with 100 base 40 cable. And from the name itself, we can see that this type of scheme can have 2 to the power of 8 equals to 256 different data patterns, and 3 to the power of 6 which is equals to 729, and these are the different signal patterns. You can have a mapping table to map between the data patterns and also the signal elements, but see that there are actually a number of redundant signal elements. You can get this by subtracting or finding the difference between the signal patterns and also the data patterns. In this case, we have 729 minus 256. You have 473 redundant signal elements, and these signal elements provide synchronization and error detection. Part of the redundancy is also used to provide DC balance. And each signal pattern has a weight of 0 or plus 1 DC values, which means that there are no pattern with a weight of minus 1. Okay, and to make the whole stream DC balanced, the sender keeps track of the weight. If two groups of weight 1 are encountered, one after another, the first one is sent as is, while the next one will be inverted to give a weight of minus 1. So that's what with the inverted we will see later in the next slide. Example of inverted, and in the example we will see 3 data patterns encoded as 3 signal patterns, and the 3 possible signals are represented as minus, value, positive, and 0. Okay, let's see an example. As you can see here, the first 8-bit pattern 001, 0001 is encoded as the signal pattern minus 0, minus 0, plus, plus. And if you add minus 0, minus 0, plus, plus, you get the weight of 0. And here is the second bit pattern 01, 01, 0011, and it will be encoded as minus, plus, minus, plus, plus, 0. And if you add the minus, plus, minus, plus, plus 0, you get a weight of plus 1. And the third 8-bit pattern is 01010000, should be encoded as plus, minus, minus, plus, 0, plus, with a weight of plus 1. So to create the DC balance, the sender inverts the actual signal at the third 8-bit pattern. Okay, so the receiver can easily recognize that this is an inverted pattern because the weight is minus 1, and the pattern would be inverted again before decoding. From here, you can also find the scenario of the scheme. Theoretically, as average equals to half n times 6 to the power of 8. Remember the equation just now. In practice, the minimum bandwidth is very close to 6n over 8. And with the mapping, if I would ask you to solve for 8B60, I will give you the mapping table where you would see for different 8-bit pattern what will be the signal pattern. Okay, so this will be given. You just need to be able to know how to do it. Okay, it's just straightforward. The last line coding or signaling scheme that we'll discuss under multi-level category is called 4-dimensional 5-level pulse amplitude modulation, or in short 4D PAM5. The 4D means that the data is sent over 4 wires at the same time, and PAM5 means that it uses 5 voltage levels such as -2, -1, 0, 1, and 2. However, one of the level 0, is just used for forward error detection. So from here, if you assume that the code is just 1-dimensional instead of 4-dimensional, the 4 levels may be created something similar to 8-bit 4Q. So in other words, an 8-bit word is translated to a signal element of 4 different levels. Okay, from this imaginary 1-dimensional version, we can see that the word signal rate is n times 4 over 8 or n over 2. And with the 4D PAM5 technique, is actually designed to send data over 4 channels or 4 wires, which means that the signal rate can be reduced to n over 8. If we compare to n over 2 just now, this is a very significant achievement. So all 8 bits can be fed into a wire simultaneously and sent by using one single element. one signal element. Okay, the point here is that the four signal elements comprising of one signal group are sent simultaneously in four-dimensional setting. Gigabit LANs use this technique to send 1 gigabit per second data over 4 copper cables that can handle 125 megabaud. If you can see that this scheme has a lot of redundancy in the signal pattern, because 2 to the power of 8 equals to 256 data patterns, and they can be matched to 5 to the power of 4, which is equals to 625 signal patterns, and the extra patterns can be used for other purposes such as error detection. So basically you can see that for level 5 is sometimes called quinary, as compared to ternary is for 3, right? So quinary pulse amplitude modulation, it uses 4 signal levels to represent 2 bits, where the 5th level provides for forward error correction. And some of the advantages of 4D PAM5 line coding can be sent over 4 channels, and the signal rate is reduced by n over 8. It has redundancy where the data is used for error detection. It offers self-synchronization, and there is no DC components in the encoded signal. Although from the redundancy, it is also a drawback, where there will be too much redundancy. Yes, I think that's all. Let's see an example for 4D PAM5. So as you can see here, on the left is actually the imaginary one-dimensional, and the actual four-dimensional implementation is on the right, where we have all 8 bits can be fed into a wire simultaneously and sent by using one signal element, and the 4 signal elements comprising one signal group, and they are simultaneously sent in 4-dimensional setting. Okay, let's start this video with data rate limits. This is a very important consideration in data communications, where we want to see how fast we can send data in bits per second, okay, over a channel. So data rate, it depends on 3 factors: the bandwidth available, the level of the signals we use, the quality of the quality of the channel, which is it means the level of noise. There are 2 theoretical formulas that were developed to calculate the data rate. One is by Nyquist for a noiseless channel, and another one is by Shannon for a noisy channel. Okay, let's start this video with data rate limits. This is a very important consideration in data communications, where we want to see how fast we can send data in bits per second, okay, over a channel. So data rate, it depends on 3 factors: the bandwidth available, the level of the signals we use, the quality of the quality of the channel, which is it means the level of noise. There are 2 theoretical formulas that were developed to calculate the data rate. One is by Nyquist for a noiseless channel, and another one is by Shannon for a noisy channel. The behavior of MLT3 is best described by the state diagram shown here on the right. The 3 voltage levels, that is negative V, 0 and positive V, are shown by the 3 states or the oval shape. The transition from one state or level to another is shown by the connecting lines. And the rules, as you can see here, if the next bit is 0, there will be no transition. If the next bit is 1 and the current level is not 0, the next level is 0. And the last rule is if the next bit is 1 and the current level is 0, then the next level is the opposite of the last non-zero level. Figure on the left, you can see example of MLT3 signal. Okay, one might wonder why we need to use MLT3, a scheme that maps one bit to one signal element. The signal rate is the same as that of NRZ invert, but with greater complexity because we have more levels, that is 3 levels, and a complex transition rules. It turns out that the shape of the signal in this scheme helps to reduce the required bandwidth. Okay, let's see an example of a worst case scenario, a sequence of ones. In this case, the signal element pattern positive V 0, negative V, 0 is repeated every 4 bits. A non-periodic signal has changed to a periodic signal with a period equals to 4 times the bit duration. So this worst case situation can be simulated as an analog signal with a frequency 1/4 of the bit rate. In other words, the signal rate of MLT3 is 1/4 the bit rate. This makes MLT3 a suitable choice when we want to send 100 megabit per second on a copper wire that cannot support more than 32 megahertz, which is the frequencies above this level create electromagnetic emissions. As you can see here, we have repetition of every 4 bits, and this is the worst case scenario. Okay, and so this is basically MLT3, and we are not going to go in depth in all of the line coding, but basically whatever is covered here will be covered in your examination. If you have any question, please do not be shy to ask me. Okay. Before I end this video, please let me know how is your understanding on this topic throughout this video so far at this link. Your participation is highly appreciated. If you have any questions or comments, please let me know. Thank you and see you on the next video.